Everyone settled? So back in January, I saw this Java coding challenge posted on Hacker News. The 1 billion rows challenge is a fun exploration of how far modern Java can be pushed for aggregating 1 billion rows from a text file. So the task is to take a 1 billion row input file of these weather station temperature measurements and aggregate them into minimum, mean, and maximum by station. You're not allowed to use any external dependencies. I thought it'd be fun to try doing this in Ruby instead of Java and see how far we can push Ruby. So this talk is about my adventure trying to optimize Ruby code to solve this problem and some of the tools and techniques I used along the way. So what sort of sizes are we talking about here? This create measurement script is from the original 1 billion rows challenge repo, and it generates an input file with a given number of lines. So we run it with 1 billion, and you get out a 13 gigabyte input file. That's kind of big enough that we should be careful about how we work with it. Like we probably want to work with it, like stream it in line by line, rather than loading the whole file into RAM at once. But it's not big data. Like it's small enough for a single machine to handle entirely in RAM. And importantly, it's small enough that the OS will be able to cache the entire file in RAM after it's been loaded for the first time. So the performance is really a question of how quickly we can process the bytes of this file on the CPU. It's not a question of how fast is our I/O, how fast is the disk. So I started with a basic Ruby implementation. It looks like this. Setting up an aggregate struct to sort of track the rolling minimum, maximum, sum, and count for each station. They get stored in a station's hash by the hash is keyed by the station name, and this is the default value. And then we open the file. For every line in the file, we split the line into name and value, and look the name up in the hash, and add the value to the aggregate. And then once we're done with the file, we sort the keys and print out the results. That all make sense?
Yep.
So we have this Ruby program, and how do we measure how fast it is? The simplest tool you can use is one you already have. It's built into your shell. You can prepend time to any command. So let's try that. So I'm running this with a 1 million line input file just for the sake of time. Like that. And then it says it took 1.298 seconds. And if I run it again, we get a slightly different answer. And again, different again. And there's some noise in the measurements. Like the computer's doing other things. Not everything's exactly the same, so it takes a different amount of time. And this can be a bit of a trap if you're doing optimization, you're trying to determine if a change you've made has actually improved something. It's very easy to trick yourself into thinking something has worked. Ideally, you want to do multiple runs when you're doing these sort of measurements and average them. There's another tool I found called Hyperfine that automates this, and it can also compare different commands and tell you how fast they are relative to each other. I'll give a demo of that in a bit. So I ran this baseline implementation with the 10 million line input file, so not 1 billion, and multiplied the result by 100. So 1,099 seconds. It's about 18 minutes. So for comparison, I also benchmarked two different Java implementations that were in the 1 billion rows challenge repo. You can go and check them out there. This like 46 second one, like kind of a middle of the road Java implementation. I'm not super familiar with Java, but it seemed idiomatic. Wasn't doing any crazy optimization tricks other than like working on the file in parallel, like putting chunks on different CPUs. And the second one was close to the top of the leaderboard. We've got a lot of work to do if we're going to beat Java. let's get the easy stuff out of the way first. Will YJIT save us from ever having to think about Ruby performance again? So I'm using Ruby 3.3, which allows us to turn on YJIT without using command line options or environment variables. You can put Ruby VM YJIT enable at the start of your program, and YJIT will be enabled. So let's compare. So we can use Hyperfine, do a warm-up run to load the file into memory, do 5 runs and run the two variants. So YJIT ran 1.17 times faster than the baseline. So that's 17% plus or minus 4%. So 17% improvement. We're just enabling a flag. It's pretty cool. Like it's pretty exciting for Ruby that YJIT enables that sort of thing. So we've got our basic implementation. We got a boost by turning on YJIT. Now what? How do we decide what to work on next? We could just stumble around and change things and hope that they make it better. But it'd be much better if we can identify what the slowest parts were, so we could target them. So enter profiling. So a profiler is a tool that helps you analyze the performance of a running program and see where it's spending its time. So StackProf and RBSpy are what's called sampling profilers. They work by periodically, like hundreds of times a second, observing the current call stack of Ruby, so what method's currently running. So let's try running StackProf. So you can run it like this. It puts its results in this dump file, and you can get a text report, or you can get a flame graph report, which looks like this. So what are we looking at here with this flame graph, if you haven't seen one before? The width of each one of these boxes is the percentage of time. So the whole program runs for 100% of time. And then these are the widths are how long each function was running for. And the y-axis is the call stack. So you can see, like, we opened the file and that was a block, and inside that block we were doing some each line. And then inside that we were doing some string split and calling aggregate add, and the aggregate add was doing some adds and comparisons. So looking at this flame graph, the slowest method we're using is string split. It's taking about 36% of the whole time. And we're also spending about 11% of the time with garbage collector. So let's see what we can do about both of these. I'm going to start by looking at the garbage. So a quick refresher on garbage collection. So in Ruby, unused objects aren't cleaned up immediately. Periodically, Ruby has to go and search for objects that are no longer needed and release them. And not all objects require garbage collection. So immediate objects like integers, floats, symbols, booleans, and nil don't need to be garbage collected. So your program stops running while the garbage collector is doing its thing. So the best way to reduce the amount of time spent doing garbage collection is to reduce the amount of garbage you allocate. Yes.
Could you just turn off the garbage?
If you have enough RAM, yes.
Do you have enough RAM?
Probably not. So that is kind of at least double it, like the size of the input file. Like it has to, like you're loading every line, and then you're probably doing some copies of the strings and
2 gig of RAM.
yeah, be close. Yeah.
I'm also thinking like the speed of RAM. Like, you can load like tens of gig a second in
Yeah.
RAM. Like, how's the program running the whole thing? And like, you can't even load it in memory that fast at 1.5 seconds. How's that work?
So the rules of the competition, I think they actually run in a RAM disk on the competition. But like even on my computer without doing that, once you run it once, like I've got enough RAM that the file will sit in the operating system's cache. We'll get to that. So you can use garbage. You can use GC stat total allocated objects to get a count of the number of objects that have been allocated in the Ruby process so far. So you can sort of run that before and after a block of code you're interested in and work out the difference, like find out how many allocations. So I measured this line, and there are 4 allocations. Has anyone got any guesses what they might be? One of them's quite tricky.
array.
Yes. That's one.
So I mean, the semicolon string.
Yes, that's the tricky one. What I haven't shown is the top of the file, and that frozen string literal thing we were just talking about is not turned on. So every time the loop runs, Ruby doesn't know that you might be going to mutate this semicolon, so it has to allocate you a fresh one. And the last two are the name and the value strings. So yeah, the array still gets allocated even though you're immediately destructuring it. So I had a go at trying to golf this and cut it down. So I ended up with something like this. So rather than using split, well, so I turned on frozen string literal. Instead of using split, I'm finding the position of the semicolon, and then using slice to pull out the value. The additional trick here is using slice bang. So we can pull out the temperature value, and then slice bang also modifies the original string, which doesn't allocate another one. And you get the name. Unfortunately, the name has a semicolon at the end now, but that doesn't really matter. It's going to consistently have a semicolon in it, so it's going to be fine in our hash. And then when we go to print it out at the end, we just chop it off. So that's reduced the number of allocations within this block to 1 to allocate a string for the value. So what has that done? Improved time by 29%. So I mentioned one of those Java programs was doing parallel stuff. Let's do parallel stuff.
Just going back on the
Yep.
validation. Do you know how many objects did you select overall? Object.
Sort of naively, if it's a billion lines and it's 3 per.
How many?
Yeah. So my CPU that I've been running this stuff on has 6 cores, 12 threads, hyperthreads, but we're only using 1. With 6 cores, we should be able to get at least a 6 times performance gain. So what are our options for doing parallel execution in Ruby? So because we're spending approximately all of our time executing Ruby code and not doing I/O, only a single thread will be able to execute at any time. So threads aren't going to help. We can do the classic option of processes. So forking your Ruby processes that all run independently. The disadvantage of something like that is you use a bit more memory, and communicating with the other processes is more expensive because you have to pipe messages back and forth. They're not sharing the same memory. And the third option is the new shiny one. Also, theoretically, this is what Raptors are good at. So Raptors, you can create multiple Raptors within a Ruby process, and each Raptor can execute Ruby code in parallel. It has its own lock, and they can send messages to each other. So this is new and experimental. So in order to go parallel, we need a strategy for dividing the work. There are a few options, each with different challenges. The first one is dividing by line. So we can go through and farm out each line 1 by 1 to the parallel workers. That's going to be super high overhead. Communicating a piece of work to the worker process isn't free. And if we have to do that 1 billion times, it's going to add up. The amount of work we have to do for each line is quite small. Another option is dividing the work by ranges of lines. So, line 0 to 10 into one process, line 10 to 20 into another process. That sounds good, but because the lines are different lengths in the file, we don't know where they start and end. So to find the 10th line, you'd have to read through the file and count new lines. So that's not going to help either. So the third option is we could do ranges of bytes. Now, the trick here is you might end up in the middle of the line. Byte 64, you're here in the middle of this line. But there's a neat trick. If for everything other than the first chunk, you just throw away until you reach, like you throw away until the first new line, and then you do your processing. And then when you reach sort of the limit of the chunk you were given, so in this case 128, you don't stop. You finish the line you're on. So then overall, you process the whole file without having to search for any line endings. So let's have a quick look at the processed version of this. So I'll get the file size, generate a list of ranges. I'm using 16 meg here. I'm using the parallel gem. So that automatically starts a worker for every processor in the computer. We take each one of these ranges and we call process chunk, which is very similar to what we had before, except we're opening the file and seeking to a specific spot. That's the trick about the discarding the first line. It's as much the same. We exit the loop when you get to the limit of continuing to the end, and we send back the aggregates for that chunk of the file. And when we do that, this finish callback runs, and that takes those aggregates and merges them into the final result. And that's pretty straightforward. The minimum of two overall aggregates is still the minimum, and same for the maximum. And then you add the sums and the counts, and then print out the result. Yes.
It's that new Ruby syntax where you can say finish colon and it's like finish colon finish.
Yes, I forget the cute name for it, but yeah, it's shorthand. It's shorthand for that. Yeah.
I don't know. It's like, yeah. Yeah.
Thank you.
Wow. Yes. I don't know.
Yeah. So, like comparing with the Java version, like Ruby's a bit over twice as slow as the middle of the road Java implementation, and that's honestly better than I was expecting. Like, this sort of CPU intensive work isn't something that Ruby is good at. So I talked about Ractors. What about Ractors? They should be faster because everything happens within the one Ruby process. It was only a 1.7 times improvement over non-parallel. My guess from what it looked like was happening is the garbage collector is still single-threaded and it lives in the main reactor. So the main reactor was really busy trying to keep up with the garbage for the 12 workers. And then all the workers were blocked waiting for the main reactor to finish garbage collection. So it's very much experimental reactors, not production ready yet.
I believe they're working on making garbage collector the Raptor.
Yeah.
Oh, it's not big.
So let's run the profiler again on the processors version, not the Ractor one, and see what the bottleneck is now. Switch to using RBSpy this time because it's got this sub-processors option that automatically keeps track of sub-processors, which is handy. So the slowest thing is now each line. But what can we do instead?
What was the difference between running parallel gem with the threads versus processes?
I didn't even try the threads. I think it would basically give no improvement. Yeah. Yeah, so I want to put in a quick mention of one of my favorite tools, which is strace. You can use it to see how a process, so any process, not just Ruby, is interacting with the operating system. There's a similar tool on macOS called dtrace. So if you run strace like this, you get a whole lot of output. There's lots showing every syscall that the process is making to talk to the operating system. And so you can see in this case where the script is mostly making read calls. That sort of ties into how is each line getting the next line from the file. So Ruby is making that read syscall, it's asking the operating system to give it the next 8 kilobytes from the file. The operating system is copying the 8 kilobytes from the file, which is already cached in RAM. We've run the thing multiple times. It's already there in memory, and copies it from RAM into an internal Ruby buffer. And then Ruby searches through that buffer looking for the next new line. And then when it finds a new line, it copies those line bytes into a string object, which it then yields to your block. And it does that over and over again until it gets to the end of the file. That's a lot of copying. We're copying from the operating system's copy of the memory into a buffer, and we're copying again. There's an alternative operating system API for accessing files called mmap, memory map, which we can use via IO buffer in Ruby. So mmap tells the operating system to use virtual memory to make the file appear within Ruby's memory without copying it. That works particularly well here because the file is fits in memory, and we know it's already in the cache. So having this IO buffer in Ruby is a bit like having a giant string for the whole file. We can get a byte at a particular index by using get value, and these are returned as integers, so there's no allocation. So a semicolon will have the ASCII value 89. And we can also slice strings out of this buffer and get a Ruby string object by giving it an index and a length. So using IO buffer like this removes the overhead of calling read for every 8 kilobytes. And we also no longer have to allocate a string for every line, because we didn't actually need that line string. We just wanted bits of it. So that looks like this. We ask IO buffer to mmap file, do the same chunk logic as before. Unfortunately, this is quite verbose now. So this is the loop where we're looking for the semicolon. So we're getting the individual characters out of the file one by one, checking.
You're getting bytes, not characters.
Yes.
Is that specified in the original thing?
It's a UTF-8 file, and you are supposed to handle UTF-8 in the names. Yeah. Yeah, it's an interesting point. I think it's safe because none of the multi-byte characters will look like. I think it's a part of UTF-8. You won't get a multi-byte character where something's not a semicolon looks like a semicolon. All the multi-byte characters are like 8-bit high ASCII characters. I think that's true. Yes. So as long as you don't mangle the bytes, it doesn't you can get away with it. So this is similar to finding the index, and then get string is sort of similar to slicing the name out, and semi is a constant at the top here, getting the ASCII value to compare it with, and then it's the same as before. You add to the hash. So how does that go? It goes slower. So they no longer have that each line overhead. We've traded for lots and lots of calls to buffer get value. So that didn't really work out. Not slow by much. So IO buffer get string until, where you start an offset and you tell it to return you a string up until some terminator character. Feels like an API that could reasonably exist in the standard library. And if we had something like that, it would make the code a whole lot more readable and hopefully faster. So I wrote a tiny C extension that adds it. So on the Ruby side, this is much nicer. In the loop, we get the name is the string until the semicolon, and the value is the string until the end of the line. C extension is IO buffer hacks. We're defining a new method on the IO buffer called getStringUntil. And getStringUntil is using the C memchar function, which searches a block of memory for a terminator character and tells you where it is. And then we use that to return a new Ruby string. So the Java 1 billion rows competition rules say you're not allowed to use external libraries. So this is kind of cheating, but whatever. Those rules aren't real. We can go wherever we want on this Ruby adventure. So how did that go? So close. We're 42% faster than the each line, but still a smidgen slower than the Java. More profiling. So the slowest things now I get getStringUntil, which is, I don't know, that's kind of the core of the work we're doing. It's the new C function we just added, the actual hot loop block, and then 2float. So 2float is 19% of time, and it's sort of a double whammy. We have to allocate a string for every value in order to pass it into the float, and then that string needs to be garbage collected. So we have access to the individual bytes via IO buffer. So what if we could just parse them directly into a number rather than going via the string? And also, the decimals always have a single fractional digit in the input file. It's part of the rules. So we don't even need floats. We could use integers and store tenths of a degree in the integer. So we've replaced 2float with this monstrosity that doesn't fit on the screen. So this takes an ASCII sequence of like 42.3 new line and turns it into an integer 423. It builds up a value by looping through every character and multiplying by 10. And then for the output, we just at the end divide by 10 and you get the same result. Just faster. It's pretty amazing that writing that in Ruby was faster instead of calling 2float. I'm not sure it's saying something really good about YJIT or something bad about how fast string 2float is. So we're now spending 34% of the self time in the loop. We've added, we've got all this code here that's managing offsets, and we've re-added all these calls to get value. What would be an even nicer API is if there were an IO buffer reader that managed the offset automatically and maybe also did the decimal to int parsing. Hang on,
It's
that one.
running a language. It's optimization.
I want to try and upstream the other one, the getStringUntil. This one maybe I'm not sure.
It's not an extension.
I mean,
That is the only feature of the
it's something you can probably do with Ruby that you can't do with Java. I think adding a feature to Java would be like a 5-year committee process, whereas you can just get a friendly Ruby committer to merge your PR. So on the Ruby side, for every chunk, we create a new IO buffer reader. We wrap the buffer, we tell it what offset to start at, and then we can just say, give me the string until the semicolon and pass the decimal to an integer. On the C side, we're defining a reader class. This is the C version of the custom parser. And this is the same like string until method as before, except we're also keeping track of the the offset within the C class rather than having to do that in Ruby. Okay, drum roll.
So.
It might be more C than Ruby, but Ruby beat Java.
But that's virtue of language. Like the C extensions are so natural to add. That you can
Yeah.
consider your-
But Java has C extensions as well.
So I did want to ask, like, how optimized do you feel like the Java versions are? Like, you've worked so hard.
Yeah.
Do you feel like they worked that up?
The 1 second one worked harder. I'm just about to talk about that.
Okay.
So what we had in the IO buffer implementation like seemed pretty minimal. Like how is this optimized Java version still like found another 18 times performance improvement? So one thing the Java implementation has done is completely eliminated string allocations from the hot loop. So they've implemented their own hash table, and rather than allocating strings to populate that, they're just looking at the bytes in the memory map. I tried doing that in Ruby. That was not faster. Like I could not write a faster implementation of hash in Ruby than the Ruby hash. The other probably biggest thing it's doing is, maybe don't get distracted by that for a second. Like we're working byte by byte. We're looking at every character, seeing if it's like the semicolon or whatever. The hyper optimized implementations like that 1 second Java one are doing bit pattern tricks like this to search multiple bytes in one operation. So like a CPU is just as fast as at operating on an 8-byte number as it is operating on a 1-byte number. So we're leaving a whole lot of performance on the table by only working one byte by byte. I can't explain how that works. There's an interesting blog post by one of the top 10 authors that goes into a bit more detail about how that works. So I've got one more implementation. Can we just gem install a highly optimized solution to this exact problem? Yes, we can. So Polars is it's a Rust library. It's similar to the Pandas data analysis library for Python. It's got bindings to lots of languages. Unfortunately, not Ruby, but there is an unofficial gem for Ruby. You require some polars. You ask to load a CSV file, group by the station name, do some aggregates by min, mean, and max, sort by the station name, and then in Ruby, we plunge it into the right output format. So this is the pragmatic software engineering solution. This is what you do at work if you're solving this problem. But one last interesting thing. It's important to keep in mind that different computers have different performance characteristics. So an optimization that might be faster on your machine might not be faster in production. And even in production, like machines from different generations might behave differently. So it's something to keep in mind. And here's an interesting example that kind of illustrates this. So I did most of this work on a desktop at home. If I compare how the desktop performs to this laptop, you can see that initially the MacBook Air, the fancy Apple Silicon, is about 20% faster. But if I keep continuously running the benchmark, the laptop gets slower and slower. Any ideas why? Yes, heat. The MacBook Air doesn't have fans, so it gets hot very quickly and has to slow down so it doesn't overheat. So optimization is all about this loop of measurement and then profiling to try and identify things you can improve, trying them out, and comparing with the baseline to see if you made a difference. There's a real readability and maintainability versus performance trade-off. You can make performance gains by hard coding assumptions like numbers only have single decimal places, and you can do unreadable bit pattern tricks. But they have a cost. You're trading off something. And I know we could have just added the polars gem and gone fast immediately, but the journey of exploring a problem like this is it's lots of fun, and I learned lots by doing it. And can you make it go faster? So all the codes are from GitHub. Thank you.
That's they're renowned for like taking things too far. Has somebody gone like bananas with like assembly or even like hardware hacking to get this thing sorted in like ridiculous time?
Possibly. There's on the GitHub discussion on the like the 1BRC repo, there's like people trying other languages. There might be some assembly stuff in there. There's certainly some very fast C++ stuff, sub 1 second.
People are like, it's like hardware minus Bitcoin. They built that.
Yes.
Why not just require object?
So the every object in Ruby from like a programmer's point of view, in the C VM is a value, and that has a particular size. I don't know off the top of my head. Certainly 8 bytes. Oh, okay. So Ruby kind of cheats, and if it can, rather than the value being a pointer to the heap for something that needs to be garbage collected, it just stuffs the integer values inside the value, and then it can just live on the stack, and it doesn't need to go be put on the heap and be garbage collected.
I remember in Ruby there is optimization that if it's a short enough string, it goes on a heap.
Yes, on the.
Did you notice that while you optimizing it?
I didn't. Yeah, the value string might fit, although I think because that was getting like sliced out of an existing string, one of the other optimizations is Ruby won't actually allocate a new string when you're like slicing. It'll just point at the old memory and say, oh, it's actually shorter.
So there's 3 levels of pointer there. So what Ryan's talking about is that the integers, the actual value integer is inside the value type. For short strings, the value would be a pointer to the Ruby heap, and the string value would be embedded in the Ruby heap.
Okay.
And then for long strings, in the Ruby heap, there would actually be no string, the pointer to the C heap. Although Ruby 3.3 has very good allocation now, so even 5 long strings can still fit inside the Ruby heap. So you wouldn't have seen probably more
Okay.
strings with well.
Yeah. But they still need garbage collection. Yes. Okay.
What were you trying to solve with the, like, how did you come across this?
I saw it on Hacker News, and I just finished Advent of Code. I'm like, I want another challenge. This is a challenge.
Have you heard about branchless programming? I don't really know
Not really.
about that, but
Yeah.
it could be a thing that like allows you to take advantage of the CPU that like how it like executes ahead of like where you're actually at. That behavior was like the problem with what were those
Spectre.
Yeah.
Spectre and
Yeah.
Delta. That like linked information about the values of processing. Yeah. That like and you the Spectre meltdown thing was that like it would like assume that it's gonna the probability of going down like some branch and if statement like it assumes that the check of the if is going to be this, so it goes down this branch, but then like it actually gets up to it and it's like, oh, actually it's the other one, and so then it actually has to go down the other branch. That's it's wasted some like so like it's like executing a head thing, the branch that never actually got run. That like so branchless programming is where like instead of using ifs, it's all in like ands and all those and that
Yeah.
sort of stuff. So like, you know, it's actually executing all of the stuff, rather than going down a branch.
Yeah.
Like with
The
how it's processing. But like with YJet, I think maybe it could compile ahead and execute that. Maybe.
I think Ruby might be like still a bit like too high level for those sort of things to start to take effect. But certainly the Java entries were getting to that level of performance optimization. So like branches become expensive, like you want to try and minimize them. That's about as much as I'm aware of. And yeah, that blog post mentions a bit. There's a really wild integer parser that's like all in bit tricks.
So I was on the Ruby bug tracker yesterday, where it was like trying to work out ways to make Redis protocol parsing faster. So I think there might actually be a market for some of these like string.parse individual IO buffer dot like parse individual etc. in the actual real world for things like Redis protocol parsing.
Yeah.
So
Submit the patch.
maybe it sends patches. Well, at least you explored the problem enough. You probably have some useful insights to find on that.
Okay, check it out.
Cool.